Alright, Chapter 4, Alternating Current Motors, Module 5, Neets, Navy Electrical and Electrical Electronic Training Series, Chapter 4, Alternating Current Motors. Learning objective. Upon completion of the chapter, you'll be able to list 3 basic AC motors, describe the characteristics each of the describe the characteristics series motor, but enable the to be the universal motor, explain the relation to the individual phase multiple phase voltage that produce the rotating magnetic fields in AC. Describe the placement of stator windings in two-phase motor, AC motors using rotating fields. The similarity difference between the stator windings in two-phase and three-phase AC motors. Similar, state the primary application of the synchronized motors. Explain the characteristics that make them suitable for the application. Describe the function that make the AC induction motor as widely used in electrical motors. Describe the difference between the rotating field of the multiple phase and the apparent rotating field of the single phase motor. Explain the operation of split phase windings in single phase AC inductors. 10. Describe the effects of shade poles in single phase inductor motors. Introduction. Most of the power generator system is shown in the float power used to AC. For the reason the majority of the motors used for the Navy is designed to operate AC. The other advantage of the use of the motor AC motors beside the available of the AC power in general, AC motors can cost less than DC motors. Sometimes the AC motor does not use brushes or commutators that eliminates many with the problem of maintenance wear and eliminates probable danger sparking. The AC motor is practically well suited with the constant speed application for the substantial speed that determines the frequency of the AC voltage applied with the motor terminals. The DC motor is better suited with the AC motor. Some use you require variable speed, as the AC motor can be made with variable speed characteristics only with a certain limit. The industrial build AC meters different in size, shape, the ratings with the different types of job. The motors are designed for use with the polyphase single-phase power system. It is not possible to heat the cover overall. The subject of the AC main motor, the only principle most commonly used is dealt in this chapter. In this chapter, AC motors will be divided into series synchronous induction motors, single-phase, polyphase motors. We'll discuss synchronized motors for purpose of the chapter to be discussed. May be considered as polyphase or constant speed whose rotors are energized with a DC voltage. Induction motors, single-phase, polyphase, but the rotors are energized with the induction are most commonly used with the AC motor. The series AC motor, in the sense of the familiar type of the motor, very similar with the DC motor was covered in Chapter 2. The variable serve a bridge between the old and new. Series AC motor. Series AC motor semi-electrical, same electrical as DC motor. Refer to Figure 4.1. Use the left-hand rule with the polarity coils. You can see the instantaneous magnetic polarity armature field opposed to each other. The motor action result. No reverse the current, reversing the polarity of the input. Note the field magnetic polarity still opposed to the armature magnetic polarity. This is because of the reversal effects on the armature of the field AC input because of the reversal, and it takes the place continuous. So you have your field coil. 4.1 AC motor series field armature. Construction of the AC motor field motor differs slightly with the DC series motor. Special metals elimination windings that is to reduce loss caused by the eddy currents. Hysteresis high resistance DC power can be used to drive AC motors series motors efficiently, but opposite is not true. The characteristic of the series AC motor, similar to those of the series DC motor, is varying speed of the machine, low speed with the large load to higher speed with light loads. The starting torque is very high. Series for the motor, you with the driving fans, electrical drove with other special appliances. Such theories that AC motors general character for the series of DC motors. The series motor have been designed to can operate with the AC and DC. AC/DC is motor is called the universal motor. It finds that we use a small electrical appliance. Universal motors operate with lower efficiency with either AC or DC series motors. They are built with a small size. Universal motors do not operate in polyphase AC power. Rotating magnetic fields. The principle of the rotating magnetic fields is the key to the operation of most AC motors, both synchronized and induction type, with the most rely on the rotating magnetic fields in the stators to cover the rotors to turn. The idea is simple. The magnetic field in the stator can be made to rotate electrically around and around. Another magnetic field of the rotor can be made to chase it by being attracted propelled by the stator field. Because the rotor is free to turn the file of the rotating magnetic field in the stator. Let's see how it's done. The rotating magnetic field is made up in two-phase, three-phase machines. To establish a rotating field in the motor steel, the number of the poles pairs must be the same as the multiple of the number of phases applied with the voltage. The poles must then be displaced from each other over the angle equal to the phase angle between the individual phases of the applied voltage. Two-phase rotating magnetic field. The rotating magnetic field is probably most easily seen with the two-phase stator. The stator of the two-phase induction motor is made up of two windings, multiple of two. They are placed in the right angles to each other around the stator. Simplified drawing, Figure 4.2 illustrates the two-phase stator. Two-phase motor stator, phase 1, phase 2, and phase 1 and phase 2A. The voltage applied in 1A and 2A are now out 90 degrees out of phase. The current flow is placed and phase is placed from each other 90 degrees. Magnetic fields generated in the coils are in phase with the respective currents of magnetic field that are 90 degrees out of phase with each other. The two out of phase magnets of the coils are exactly axes are at right angle to each other and add together every instant during the cycle to produce a resultant field, but the resultant rotates one revolution each cycle of the AC. To analyze the rotating magnetic field, two-phase stators refer to Figure 4.3. They are represented for the rotor for each point of the set upon the voltage of the current flow in the direction, while the colors of the magnetic polarity indicate each of the pole pieces. Note that one point of the next cycle, the polarity is rotating the one pole next to the clockwise manner. One complete cycle, the input voltage produces 360 degrees rotation polarity. So let's see how the result is obtained. Shows the phase 1, phase 2, two-phase rotating field. Waveforms in Figure 4.3 are two input phases displaced 90 degrees because of the way they generated two-phase alternating waveforms are numbered in the match of the associated phase. Although the not in figure with the windings poles of 1A and 2A would be shown in the previous figure. As position 1 current flow with the magnetic field in winding 1A is at the maximum because of the phase voltage. The maximum current flow with the maximum field rating of the 2A is 0 because the phase voltage is 0. The resultant magnetic field is therefore the direction of 1A. Access the 45-degree angle. Position 2 resultant magnetic field lies midway between the windings of 1A, 2A, and the current coil magnetic fields are equal in strength with 90 degrees. Position 3, magnetic field winding 1A is 0. The magnetic field winding in 2A is maximum. Now the resultant of the magnetic field lies across the axis of 2A with the winding is shown. The resultant magnetic field of the co-rotate with the clockwise through 90 degrees to get the from position 1 to position 3. The two-phase voltage has been completed one full cycle. Position 9, the resultant magnetic field has rotated 360 degrees, thus by placing two windings right angles to each other, the exciting windings with the voltage 90 degrees out of phase and the rotating magnetic field result. Alright, two-phase motors are rarely used except for the special purpose equipment. They are discussed here with the understanding that rotating fields will have an encounter with a single-phase of the three-phase motor. Three-phase rotating field with the three-phase induction motor with the operated with the principle of the rotating magnetic field. The following discussion shows how the stator winding can be connected to three-phase input and have the resultant magnetic field that rotates. Figure 4.4 views the AC that show the individual windings of each of the phase. Figure 4.4 view D shows how the three-phase is tied together in a Y-connected stator. The dot in each of the diagram indicates the column pointing to the Y connection. You can see the individual phase readings are equally spaced around the split stator and placed with about 120 degrees. Phase 1, Phase 2, Phase 3, and then you have 1, 2, and 3. Y three-phase Y-connected stator. The three-phase input voltage stator with the Figure 4.4 shown in Figure after 4.5. Use the left-hand rule to determine the electromagnetic polarity of the poles given the instant with applying rules and coils. Figure 4.4 current flows toward the terminal numbers for the positive voltage away from the terminal number to nominal voltage. 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7 phases. Notice that they are kind of in phase. The result of the result analysts show that the voltage of the points 1 and 7 through 4 and 5, the point 1 magnetic field, the 1A maximum polarity is shown at the same time. Negative voltage are being felt with the 2A and 3A. Winding these create the weaker magnetic field, which tend to aid the 1.1 field with the 2 maximum negative voltage is being felt with the 3A windings. This creates the strong magnetic field within term of the A, but the weaker field, the 1A, 2A, each of the point of the voltage graph and analyzed it has been a resultant magnetic field rotating in clockwise direction. When three-phase voltage completes one full cycle, the 0.7, the magnetic field has been rotated through 360 degrees. Alright, your rotator behavior, the rotating field. The purpose is explained with the rotor removed, assuming that we can play with the power magnet. Center of the stator diagram, Figure 4.5, well, none of the magnet is is free with the rotate with the air. Let's assume the power magnet is applied aligned with the point 1, the south pole opposite the large north over the stator field. You can see the alignment of natural and like pole natural. The two poles will attract, the two fields aligned so that they are attracting. Now go through from point 1 to the point 7 and as before the stator field rotates clockwise with the power magnet free with the move of the field. Follow the stator field with because of the traction between the two fields. Continuous as this shaft running through the pivot point, the bar magnet will rotate at the same speed of the rotating field. The speed known as the synchronizing speed shaft represents the shaft of the operating motor to which the load is attached. Remember, the explanation of the oversimplification is meant to show how the rotating field causes mechanical rotation of the shaft. Such arrangement would work, but is not used. There are limitations. Permanent magnet motor. Practical motors use other methods, so as which we see the next paragraphs. Alright, your synchronizing motor. Construction of the synchronizing motor is essentially the same as the construction of the salient pole alternator. In fact, the alternator may be run into the AC motor. Then, similar drawing figure of the figure 4-6, synchronizing motors have the characteristic constant speed between no load and full load. They are capable of carrying a low power factor, introducing inductive load when they are operated under certain conditions. They often use to drive a DC generator. Synchronized motors are designed to size up the house 1,000 horsepower. They may be designed each either single phase, multiple phase machines, and the design that follows be based on the three-phase design. To understand how synchronizing motor works, assume the application of the three-phase AC power is a state that causes the rotating magnet field to be set around with the rotor. The rotor is energized with the DC. It acts like a bar magnet, storing rotating magnet field correct with the stator hung or rotor field activated by the DC. Result of the strong force turning on the rotor shaft. The rotor is thereby able to turn the load rotates in step with the rotating magnetic field. It works with the way the one started. However, one of the disadvantages synchronizing motors is they can be started. It cannot be started by a standstill by applied three-phase AC power to the stator, which AC is applied with the stator. High-speed rotating magnetic field appears immediately. Rotating field brushes through a path of the rotor pool so quickly the rotor does not have a chance to get started. In effect, the rotor is repelled in first one direction, then the other. The synchronizing motor, in purest form, has no starting torque and is in torque only with the running of the synchronizing speed. A squirrel cage type of winding is added to the rotor synchronizing motor to cause it to start. Squirrel cage is known as the outer part of the rotor's figure 4-7. It is also named because of the shape and look the same as something like a turntable. Squirrel cage simply winding is over the heavy copper bars shorted. Together, copper rings low voltage induced, and these currents are winding the rotating three-phase of the stator fielding. Because of the short circuit, the relatively large current flow of the squirrel cage that's caught with the magnetic field that interacts with the rotating field of the stator. Because of the interaction with the rotors being turned following the stator, the motor will run into the squirrel cage again. In other applications, will be covered in more detail. Or it shows the squirrel cage winding over salient pole windings. To start practical synchronizing motors, the stator energized with the DC power supply with the rotor field energized with the squirrel cage winding, bringing the rotor to the near synchronizing speed. At this point, the DC field is energized, lock the rotor in step with the rotating stator field. Full the torque is developed and loading is driven. The mechanical switch is developing, operating on the central figure of force often used to apply the DC motor rotors and synchronizing speed reduced. Practical synchronizing motor with a disadvantage requiring the DC AC voltage rotor with the voltage must be attained externally, internally, depending on the design of the motor. Your induction motor. The induction motor is most commonly used with the type of the AC motor. Simply rugged construction costs relatively little or manufacturing. Induction motors has a rotor that is not connected to the external source of voltage. The induction motor derives named over the fact that the AC voltage induced to the rotor circuit with the rotating magnetic field of the stator. There are many of the ways of the induction of the motor is similar with the induced primary and secondary windings of the transformer. Large motors, permanent mounted motors that drive loads fairly constant speeds are often induction motors. An example found in washing machines, refrigerator compressor, bench grinders, and table saws. Stator construction of a three-phase induction motor with a three-phase synchronizing motor are almost identical. However, the rotors are completely different. The induction rotor main laminated cylinder with a slot with a surface windings. But these slots are 1 and 2 types. Shown figure 4-9. The most common squirrel cage winding, the entire winding is made up of the heavy copper bars connected with each other and metal ring with a copper brass. No insulation is required between the copper and the bars because there is very low voltage generated. The rotor bars, other type of windings contain the all actual coils, rotor slots, and motors is connected to the wound rotor. Shows the induction motor, also the squirrel cage rotor with metal ring, laminated core, copper bars, and your wound rotor coils, laminated core. Regardless of the type of the rotor, the basic principle is the same. The rotating magnetic field generates the stator induced the magnetic field in the rotor. Two fields interact and cause the rotor to obtain the maximum interaction between the field. The air gap between the rotor stator is very small. As you know, the Lenz law introduces the EMF to try to impose the changing field that induces it. And in this case, the induction motor, the change field in the motion of the resultant stator field, the force is exerted with the rotor inducing the EMF of the resultant magnetic field. The force tends to cancel the relative motion between the rotor and stator field. The rotor's result move in the same direction as the rotating rotating stator field. It is impossible to rotate the induction motor at its turn special on the same speed of the rotating magnet field, but the speed of the magnet were the same. There would be no relative motion between the stator and motor fields. Without relative motion, there would be no induced voltage in the rotor. In order to the relative motion to exist between the two, and rotors must rotate speed slower than the rotating magnetic field. Thus, the difference between the speed of the rotating stator and the rotor speed is called the slip. The smaller the slip, the closer the rotor's speed approaches the stator field speed. The speed of the rotor depends on the torque requirements of the load. The bigger the load, the stronger the turning force needed to rotate the rotor. Turning the force can increase the rotor, induce the EMF, increase the EMF, increase the E only. With the magnetic field cuts through the rotor is faster, the rate, and increase the relative speed between the feeder and the field and the rotor. Rotor must slow down, therefore, the heavier loads, the induction motor turns to the slower, the lighter loads. You can see that the previous alignment of the slips directly proportional load on the motor. Actually, only a slight change in the speed necessary to produce the useful current change required by the normal change in the load. This is because the rotor windings have so much low resistance. As a result, induction motors are constant speed motors. Are your single-phase induction motors? There are probably more single-phase AC induction motors than used today until all the other types to put together. It's logical and less expensive, lowest maintenance type of the AC motor should be used the most often. Single-phase induction motor fits its description. Unlike polyphase induction motor, the stator field in the single-phase motor does not rotate. Instead, it simply alternates polarities between the poles of the AC voltage change of the polarity. Voltage induced in the rotor, a result of the magnetic field produced around the motor. The field always by the opposition of the stator field. If the Lenz's law applies, the interaction between the rotor and stator fields will not produce rotation. However, the interaction should be double-ended arrow with the figure 410 view A, because the forces across the rotor through the pole P for the rotor motion just pushes and pull along this line. Show the stationary rotating number of rotaries, stator rotary field, number of stator field, number of stator field. Right, now that if they rotated by some other outside force, twist of the hand or something, the push of the pole along the figure 410 view A with the distributed look at the field of the shown figure 410 view B, instance south pole with the rotor being attracted with the left hand pole, the north rotary pole is being attracted with the right hand pole. Along this result, the rotor being rotated 90 degrees, but the outside force of the pole now exists between the two fields, between the rotary force returning the rotor toward the magnetic coordinates with the stator. Because the two fields continuously alternate, they will never actually line up. The rotor continue to turn once started remains for use of learning practical methods of getting the rotor to start. There are several types of single-phase induction motors in use today, basically identical, except for the means of starting. In this chapter, we discuss the split-phase and shade pole motors, so that named because of the methods employed to get them started. Once they are up to operating speed, all single-phase induction motors will operate the same. Your single-phase induction motor, one type of the induction motor, it will incorporate the start of a device called a split-phase induction. Split-phase motors are designed to inductance, capacitance, resistance, develop starting tongue of torque. The principles of those learned in studying alternating current. Capacitor start. The first type of the single split-phase inductor motor will be covered by this capacitor starter type. Figure 411 shows the simplified schematic of the typical capacitor starter motor. The stator consists of the main winding of the starting the winding. Auxiliary start winding is connected with the parallel main winding of the place in physical right angles and 90 degrees electrical. Phase difference between the two windings is obtained with the connection of the auxiliary winding and the shear of the capacitor starting the switch of the motor. First energize the starting switch is closed. The phase capacitor and the shears of auxiliary winding of the capacitor is such value the auxiliary circuit is actively resistive. Capacitive circuit referred to as capacitive reactance, expressed in the capacitive reactance, and then the circuit of the current field line voltage of 45. The capacitive reactance equal to a resistance. The main winding has enough resistance induction referred to the inductance resistance expressed as in XL to cause the current to lag with the line voltage of 45 degrees. The inductive reactance is equal to resistance, about equal to resistance. The current is each winding is therefore 90 degrees out of phase, so that their magnetic fields are generated. The effective of the two final windings of the like two-phase stators produce the rotating field are required to start the motor. 411 shows the capacitor starter at AC inductor, the AC single-phase single supply, auxiliary winding, main winding, a capacitor. When nearly full speed, obtain with the central figure device starting switch cuts out the starting winding of the motor, then runs the plain single-phase induction motor. Starting since the auxiliary winding is only with light winding. The motor does not develop sufficient torque to start the heavy loads. The split-phase motor therefore comes in only small size. The resistance start. Another type of split-phase induction motor, the resistant start motor with the motor has start winding and additional with the main winding. The switch with the in and out with the circuit adjusted as the capacitor starter motor. The starting winding is positioned right angle to the main winding. The electrical phase shift between the currents of the two windings and obtain to make the impedance of the winding unequal. Main winding of the high inductancy, low resistance. The skinner of the therefore lags the voltage at a large angle with the start winding with a design fairly low inductance, high resistance. Therefore, the current lags the voltage with a small angle. For example, suppose the current of the main winding has lacks voltage of 70 degrees. The current auxiliary winding lags the voltage of 40 degrees. The current, therefore, out of phase at 30 degrees. Therefore, the maximum field, magnetic fields out of phase are the same amount, although the ideal angular phase difference is 90 degrees. For the maximum starting torque, the 30-degree phase difference still generates rotating field that supplies each of enough torque to start the motor. When the motor comes up to speed control switch disconnects the started winding from the line with the magnet. The motor continues to run is the induction motor, and starting torque is not great enough to in the capacitor starter. Figure 412 shows the resistance starting AC inductor motor and AC single phase, the resistor auxiliary winding, main winding, rotor. Alright, your shaded pole induction motors. Shaded pole induction motors are another single-phase motor that is uniquely method to start with the rotor, earning the effect of the magnet field produced with the construction in a special way. Motor has the projection pole produced just like DC motors. In addition, portion of the pole piece surfaces with the surrounded with the copper strap called the shading coil. A pole piece of the strap is placed in shown figure 412. The strap that causes these fields to move back and forth across the face of the piece of the pole piece, but note the numbered sequence points with the magnetizing curve on the figure. The alternating stator field starts to increase to zero. The lines are forced to expand across the face of the pole piece, cutting the strap. The voltage induced with the strap, the current that result of the generator field with the output and the current of the action decrease the strength with the main field with producing the following action. Field increase to zero, the maximum 90 degrees, large potential magnetic lines field. Or is concentrated on unshaded portion of pole 1. If 90 degrees field reaches the maximum value, start the lines force have been stopped. Expanding no EMF induced the trap, no opposing the magnetic field and generated as a result the magnetic field and the main field. As a result, the main field uniformly distributed across the pole 2 from the 90 to 180 degrees. The main field starts to decrease with the collapsing inward field generator and strap, opposing the collapsing field with the effect of the concentration of the line of the force over the shaded portion. Pole face 3, you can see that 0 to 180 degrees main field shifted across the pole face from the unshaded portion of 180 degrees, 360 degrees. Main field goes through the same change as it did 0 to 100 degrees. However, note its opposite direction for the direction of the field does not affect the way of the shade pole works. The motion of the field same during the second half cycle it was during the first half cycle. Figure 413 shows the shade pole, using the shade pole AC inductor motors. The motion of the field back and forth between the shaded and unshaded portions produce the weak and the torque of the start of the motor. They cover the weak and the starting torque of the shaded pole motors are built only in the small size. They derive the such devices, fan clocks, blowers, electrical razors. Speed single-phase inductor. Speed inductor motors depending on the motor side of the synchronized speed. The speed at which the stator field with the rate rotates to determine the frequency of the input at the AC power number of the poles in the stator. The greater number of the poles, the slower the synchronizing speed. However, the frequency will apply with the voltage. Higher the synchronizing speed. However, neither the frequency nor the poles are variable. They are both fixed by the manufacturer. Relationship between the pole's frequency and the synchronizing speed is as follows: the number of revolutions per minute. Where n is the synchronizing speed and RPMs, F is the frequency applied with the voltage in hertz, and P is the number of the poles in the stator. You get the number of synchronized speeds and RPMs, the 120 degrees and frequency of hertz, and the over the number of poles. Let's see the 4 poles the built and the 60 hertz. The synchronizing speed determined is 120 degrees, 120 times 60 over the 1800 RPMs. The common synchronizing speed for 60 Hz motor 3600, 1800, 1200, 900 RPMs depend on the number of the pole's original design. As we have seen before, the rotor is never able to reach synchronizing speed. If you don't know whether no voltage would induce the rotor, no torque would be developed, the motor would not operate. The difference between the rotor speed and synchronizing speed is called the slip. The difference between the two speeds is not great. For example, the rotor speed 3400, 3500 RPM can be expected. The synchronizing speed of 360 RPMs.